Hi everyone. So in this lecture we have a complete shift. This is where the term really cleaves into two pieces. So prior to this we talked about electromagnetism and relativity. Now we're going to talk about quantum mechanics and nuclear science, and those are really two very distinct subjects. So in a sense, reboot, we're starting over again, and we want to talk about quantum mechanics. So quantum mechanics is the study of little itty-bitty things. We're really talking about atoms, atomic size things that also has implications in solid-state physics, transistors, the construction of integrated circuits and things like that. Anything that's very small, sub-microscopic, really. If you can see it with a microscope, quantum mechanics is not going to come into play. So, as people were investigating the nature of atoms and how things work on a very small scale, things got very weird very quickly. Around the turn of the 20th century, in about 1900, there's a guy named Max Planck who was investigating some issues in thermodynamics, basically he and Einstein together kind of came up with this idea that light, which we've talked about as an electromagnetic wave, actually has many characteristics that make it seem like it's a particle. And one of those is the fact that it has momentum. It's got a punch behind it. And we talked about the fact that it really is connected to the fact that E equals mc squared. Electromagnetic field has energy associated with it, so you'd expect energy or radiation to have a certain amount of momentum associated with it. However, as people started to investigate atomic nature and things like that, a similar kind of idea came into play where, it seemed more and more like particles, electrons in particular, surrounded by an atom, that as these electrons were confined around the atom, they had a lot of properties that made people think maybe this is acting more like a wave. There's vibration, there's patterns here, there's restrictions that are associated with it, much like the way in which harmonic frequencies are created. There are certain resonant frequencies at which waves magnify, and the same thing seemed to be happening with electrons. And so there's this notion of a wave-particle duality, and that really sits at the foundation of quantum mechanics. Every particle has both particle and wave-like characteristics to it. Kind of in a fundamental sense, it's really not proper to talk about the electron as a particle. We really talk about it as a quantum mechanical field. And that quantum mechanical field, kind of in analogy with the electromagnetic field, has particle properties associated with it. In the same way, the electron has particle properties associated with it. But in a sense, it's probably easier for you to throw out the idea of particles and think more in terms of fields. Although, we will go back and forth quite a bit. We'll talk about the electron as if it were a particle, and a particle moving through space. But really, at a fundamental mathematical level, we've got fields that act like waves and particles. And one of the consequences of that is called the Heisenberg uncertainty principle down here. So if this is kind of a new mental picture for what an electron looks like, it doesn't really have a specific location in space, right? There's a peak, and so this is the particleness, but it's also got a certain spread associated with it. And where does it stop spreading? Well, it's arbitrary, right? And mathematically, it extends out to infinity. But Heisenberg came up with this notion, or it's kind of a consequence of the wave-like nature, is that the faster a particle, a packet moves, the the more we restrict the location of a packet, the less we know about its speed and momentum. In other words, the more we know about where a particle is, the less we know about its momentum. And in a sense, what I'm saying is that the more we constrain this packet, we lose kind of that ability to measure its momentum. And that's where this is fundamentally coming from. There are a lot of analogies possible between physical and geometric optics. So we know that light is fundamentally an electromagnetic wave. Therefore, that's where the physical optics come into play. But we also know that there is a limit in which we can talk about light as if it were a ray, almost like a particle of light, right? And we know that that occurs when the obstacles, the characteristic distances are much larger than the wavelength associated with the waves. Well, actually, there's an analogy between quantum mechanics and classical mechanics where we've got this formula which represents the quantum mechanical wave. If we're talking about large objects, the interaction, that reduces down to quantum mechanics in the same way physical and geometric optics are related. There is a characteristic wavelength, therefore, associated with every single particle. That's called the de Broglie wavelength. And that's given by this formula here. And this argument here just represents the fact that you can derive the same formula for light. What de Broglie did was he said, this relationship between wavelength and momentum for light, maybe it's true for everything. Maybe it's true for particles as well. Maybe an electron has a characteristic wavelength which is inversely proportional to its momentum. And that is the de Broglie wavelength, and that is really at the foundation of quantum mechanics. And it is one way of understanding why distance, or position, and momentum are inversely related, because wavelength and momentum are inversely related in the de Broglie wavelength.